Hello everyone, I am Zach Peterson. Welcome back to my channel. In this video, we're going to be looking at a very important PCB design topic, which is near and dear to my heart, and that is the accuracy of PCB via impedance calculators. Now, if you work on high-speed PCB design and you're doing anything with digital signals that require channel bandwidths reaching into the tens of gigahertz range, then you should know that you will need at some point to match via impedance to your trace impedance, especially for differential vias. Now, I received a question about this just recently in my LinkedIn inbox, and we do have another video that will be coming out soon about this topic, but I wanted to address this particular topic because I think most people will start looking at free via impedance calculators on the internet to try and figure out the answer to this problem. And unfortunately, those via impedance calculators are wrong. We're going to detail why that's the case and how you can get to the correct via impedance in this video. Let's go ahead and get started. So the topic of this video is via impedance and whether or not you can trust via impedance calculators that you find on the internet. There are also two well-known companies that produce via impedance calculators, and they're very simple calculators, and we'll see why they're so simple and unfortunately incorrect once we get into this video. But first, I want to take a look at a LinkedIn post because this whole topic came to my attention because I was recently tagged in a LinkedIn post by someone I'm connected with. Paul Clark writes, "Just when I felt I know what I'm doing with impedance-controlled differential pairs, I have just finished reading Donald Tellion's new book, Signal Integrity in Practice, which he recommends, and started wondering about how I run differential pairs. The main thing that tipped this off was the impedance in via holes. Donald suggested that an 8mm hole gives you just under 100 ohms impedance and was a nice choice as you then have about a 10mm pad and anti-pad, keeping the differential pairs nice and close. So I'm wondering if I'm running a 100 ohms differential pair at 50 ohms each odd mode impedance. When you reach the via holes, are they 100 ohms each? But they are not as close together as the differential pair tracks were. So does that mean they cancel out? I had a skim of both Eric Bogatin's book and also looked on Sierra Circuits, but could not see a clear answer. So I'm interested in your views on this. Maybe Zachariah Peterson will explain it to me in a video, LOL. Well, Paul, I am happy to make that video for you, and we're doing it right now. So first, let's answer the core of your question, which is what happens when you fan out the traces into a pair of vias. If you go back to the LinkedIn post, you'll see here that we have an image attached to this LinkedIn post, and it shows you what happens when a differential pair routes into a set of vias. Of course, you can only put those vias so close together, and the reason is, of course, manufacturing constraints. There has to be some minimum distance between the hole wall on this top hole and the hole wall on this bottom hole, and that could require you to break those tracks out a little bit in order to route into those vias. Then once you reach the destination layer, you break those tracks back in towards each other to get back to your coupling distance, and then you continue on routing as normal. Now, the first thing I'll point out in this image is that you have your tracks pretty close together in the image, and this implies that you are relying on tight coupling. But if you remember some of my other videos about differential pairs, as well as some of the advice from folks like Rick Hartley, the tight coupling that you have in this image is not required. And in fact, if you use thinner dielectric layers, which are better for EMI, then you should also require a larger spacing between the traces in your differential pair. So that's going to reduce the impact of fanning out the traces to reach the vias, and then it will reduce the deviation in the input impedance looking into the via transition. So that addresses the question about the fan out, but what about the impedance of the via holes themselves? Well, those via hole impedances also need to be matched to your trace impedances in order to ensure that you don't have any reflection at those vias. But what's important is not just the via impedance itself, it's actually the input impedance into the via, and I've explained this in a comment on your LinkedIn post. Let's take a look at my comment as well as some of the other comments from folks on LinkedIn. My comment is very simple. What matters is the input impedance looking through the via holes. And Donald Tellion is right, particularly at low enough frequencies. If you're below about 3 to 5 gigahertz, because at those frequencies, the vias basically appear invisible. See critical length rule or Dawn's relative feature size rule. And as long as the via spacing and antipad are not too small, then anything goes. Now, I'll leave it up to viewers on this video to read the rest of my comment, because I go into some design points about 224 gigabit per second lanes and what's needed to get to 448 gigabit per second lanes, particularly regarding via transitions. So I'll show some slides later in this video that shows what's wrong with the traditional via impedance models and what vias actually look like if you want to place a via on a differential pair that's being used for 224 gigabit per second per lane routing. Let's take a look at some other comments on this post. Praveen Bhatt writes, "You can't completely mitigate such things in the layout, but try to keep via as close as manufacturing allows. Add return path via near both vias. Impedance discontinuity in a small area is negligible unless it's a very high speed signal." Well, I think there's a little bit of overgeneralization here. You should size the spacing between the vias so that you hit the target impedance within your channel bandwidth. You shouldn't just try to put them as close together as possible. You also have the option, as I mentioned earlier, to widen out the spacing between your traces. If you move your traces out from each other, you don't have to put the vias closer together, and that might be exactly what you need to make sure that you have an impedance on the via holes that matches the impedance of your traces. One thing that Praveen Bhatt brought up was putting stitching vias near the signal transition vias. We have another comment on this post that actually references the same thing. Mohammed Q writes, "Pardon my limited knowledge, but shouldn't you first place a pair of return vias nearby?" In reply, Dan Chirpich writes, "Mohammed, if you care about reference integrity and localizing the energy, yeah, especially since there's some amount of high frequency common signal on those two vias." Dan Chirpich is pointing out the correct usage of stitching vias on a differential via transition when the antipad is small. And you can see that in the other video that I've referenced and which we'll have linked in the description. Now, when you have stitching vias on a pair of differential signal vias, the function of those stitching vias is to confine the electromagnetic field around the signal vias. That is the entire point of those stitching vias. You don't need them for a return path. However, they can influence how you can find the electromagnetic field around those signal vias, and that's very important for via-to-via crosstalk in differential pairs. Now, I think in this situation, most designers would try to find an online via impedance calculator that they can use to assist in the design of this differential via transition. Unfortunately, the calculators that you'll find online are incorrect. They do not correctly produce the frequency-dependent behavior in the impedance spectrum for differential via transitions and for single-ended via transitions. So what we're going to do now is take a look at some slides that illustrate what is wrong with the traditional via models. And then what we'll do is we'll take a look at what some via calculators say about via impedance, how this affects the input impedance, and then what does the impedance actually look like for a differential via transition. So here on screen, I've pulled up some slides from my PCB West 2023 presentation, and I've also presented this information at PCB East. So if you come see me at PCB East this year, I will go into some of this data live in person. Now, first, let's look at what determines via impedance. Now, you have several ways that you can model the via impedance just by looking at this slide. And generally, what we're looking for is the S parameters for this via transition as you look from the top to the inner layer or from the inner layer to the outer layer. So here we have capacitance from the via barrel to the nearby antipad or to the plane edge. There's also capacitance between the pads on the top and the bottom side of the via. You also have the inductance of the via. Of course, the via is barrel shaped, and so that implies that it has some inductive behavior. Now, all of this behavior sums together to give some complex frequency dependence for the impedance of this via. And it is that frequency dependence which online and via impedance calculators fail to capture accurately. So there is a lumped element model that has been published by Howard Johnson, and you probably know that name if you're familiar with PCB design, because Howard Johnson is the author of the Black Magic textbooks on high-speed PCB design. And in his Black Magic textbook, he brings up a via impedance model where the via is essentially modeled as like a pi filter, which you can see here on screen. Now, in this pi filter, you have some capacitance, and so you have some inductance for these vias. And the via capacitance and via inductance can be approximately calculated just using the dimensions here. So if you take the via capacitance and the via inductance, you can use that ratio to calculate a via impedance. You can also calculate an approximate propagation time for the signal to propagate between the two traces along the via, and that's given by this quantity here on the right side of the screen. So this initially looks like we have a decent model for understanding how the signal propagates along the via. The problem with this model, and the problem that all of these via impedance calculators conveniently ignore, is that the author of the model literally tells you that the model is incorrect and cannot properly model what happens at high frequencies. Why does the lumped element model fail? There's no frequency dependence, as I mentioned before, and we should reasonably expect some frequency dependence just given the capacitive and inductive nature of vias. There's no consideration of any sort of resonant modes. It grossly overpredicts the via propagation delay, and in fact, if you just plug in some numbers into the propagation delay, you'll see that it really grossly overpredicts what the propagation delay should be. It's also unable to account for things like stubs, whether you have blind and buried vias, things like that. And finally, it's only good for single-ended vias. So of course, you couldn't even apply this model to a differential via transition unless those vias were spaced very far apart such that they don't have any appreciable capacitance between them. Now here I have a quote on screen from Howard Johnson directly from his Advanced Black Magic textbook, and he writes, "If your signal rise time shrinks to a value comparable with the via delay, the signal behavior becomes extremely complex. First, to precisely predict the behavior, you will need a highly detailed model. Second, whatever you do, it won't work very well. Third, you should circumvent both problems by using a smaller via." If the guy that came up with a via impedance model is telling you that the model is inaccurate and effectively wrong, you probably shouldn't use that model. I guess the companies that produce these via impedance calculators didn't really get the memo. So now that we know what the via impedance model is, let's put it to the test. Let's head over to Sierra Circuit's website and let's take a look at their via impedance calculator and see what kind of result it gives. Then we can take that, use it to calculate an input impedance, and then we'll see if it accurately captures the frequency behavior that's experienced by signals transitioning through vias. So here I am on Sierra Circuit's website, and you can see here that we have a graphic for a through-hole via transitioning through a 4-layer board. Now, these through-hole vias and 4-layer boards, of course, we have several parameters that we would need to specify here. And I will say Sierra Circuits has improved their via impedance modeling that they've attempted to do ever since they first came out with this calculator. Previously, when they first came out with the calculator, there was just a 3-layer model where they were transitioning through one plane, and here you can see that they're transitioning through 2 planes. Now here, if we just plug in some values, for example, for the thickness of the dielectrics, and then let's say we maybe take this and make this about a 62 mil board, we go ahead and hit calculate, we can see what the characteristic impedance of this via is estimated to be. So here we have a 10 mil diameter via. Here we have 10 mils of clearance from the via wall to the nearest plane, so that gives us a 30 mil antipad diameter. And then here we have 18 mil pads. So with these 18 mil pads on a 10 mil via, you can see here that the characteristic impedance comes out to basically 37 ohms. Now, if this were a single-ended high-speed interconnect, we would of course be targeting 50 ohms for most interfaces. Or if we were doing something with, for example, DDR, we might be targeting 40 ohms, 44 ohms, 48 ohms, depending on the drive strength. Now, obviously, this impedance calculator gives us a via impedance, but the via impedance isn't actually what matters. What matters is the input impedance looking through the via to the destination trace. So what I've gone ahead and done is created an input impedance calculator here in Microsoft Excel. And for folks who have seen any of my other videos, you know I'm a big fan of Microsoft Excel calculators. Here in this calculator, we're calculating the input impedance given a via impedance Z0 here in column D. And then we have trace impedances on the input and output side. So let's plug in the 37 ohms that we calculated from Sierra Circuit's impedance calculator, and let's see what the input impedance looks like. So here you can see in this chart that the input impedance looks capacitive up to some high frequency above about 20 gigahertz, and then it appears inductive again, and then rises up to the target value of 50 ohms. Now let's zoom in just a little bit and see how well this captures what happens at low frequency. If I put my high frequency limit up to 10 gigahertz, you can see here that the via input impedance does deviate from the target value of 50 ohms and eventually drops down to 40 ohms by the time you get to 10 gigahertz. So that's a 20% deviation. Now this confirms the point that I mentioned in my comment on the LinkedIn post. If you're operating with signals that require less than 3 to 5 gigahertz of channel bandwidth, the via impedance is not going to matter at all, because you can see here in this graph that the input impedance is already very close to 50 ohms. So that's one point that really matters here in this discussion on via impedance calculators. Even if you did design a via with an impedance that reaches, let's say, 50 ohms using one of these free calculators, it's only going to be accurate in the frequency range where the via impedance doesn't even matter and all the vias already look invisible to your signals. Next question we have to ask is whether or not this high frequency behavior is actually correct. Well, I can tell you that unfortunately, this high frequency behavior is not correct. And I'm basing this off of experience working with 3D simulations of via impedance. We can use a more accurate tool that actually does perform or base its calculations on 3D models or 3D electromagnetic models of via impedance. And one of those tools is Simbeor. So let's take a look at some results that I've produced with Simbeor for much higher bandwidth channels. Let's go back to the PCB West slides here for just a moment. Here I have on screen an example showing what happens when you have vias that are targeting very high frequencies and what happens when you adjust the size of the antipad and the location of the stitching vias. So here on the left-hand side, we have a buried via transition between two layers. We're starting on layer 4 and then ending on layer 6. And here in this panel, you can see that we have our two signal vias forming our differential via transition, and then the green area around them is the antipad. So that antipad gets very close because we've removed the non-functional pads on layer 5. Then we have some stitching vias around this via transition. So with this antipad being very close to the via wall, you can see here what happens to the input impedance of this via transition in the bottom graph. You can see here that initially this via transition looks like it hits its target of 90 ohms. But once you get above about 5 gigahertz, that input impedance starts to deviate and starts to drop to a very low value. That's going to mean that this via, it starts to appear reflective at very high frequencies. Now in the right-hand side, we see a redesign of this via transition. Here, all we've changed is the location of the stitching vias, the size of the antipad, and which layer we land on in this 18-layer stack-up. Now you can see here that by changing these parameters, if we're starting on layer 4 and ending on layer 7, we would expect the via impedance to be about 90 ohms all the way up to very high frequencies. Now even if we were going in reverse, we were starting on layer 7 and we were ending on layer 4, you can see here in the red curve in the bottom right-hand side of the screen that the via impedance is still pretty close to 90 ohms. And in the worst case, we have almost a 10% deviation, but then it rises back to the target impedance. Now, what are these vertical green lines in these graphs? Well, the vertical green lines show localization, and it basically shows the maximum frequency at which this via structure can contain the electromagnetic field around those signal vias. So that's the real important point of having these stitching vias with a small antipad. The antipad will have the biggest effect on the differential impedance, while the stitching vias will help determine the localization at high frequencies. The improvement in the impedance matching for these via transitions is also reflected in S-parameter data, and you can see here that we're targeting very high bandwidth channels for 224 gigabit per second interfaces. Here you can see that at the Nyquist frequency of 56 gigahertz, the old vias have their return loss spectrum rising above a negative 10 dB threshold. So they're going to appear quite reflective up at these high frequencies above about 30 gigahertz. Now, with the newly designed vias, you can see that the return loss stays below a negative 10 dB threshold all the way up to the Nyquist frequency. So these vias are going to be acceptable for use in very high bandwidth channels, and they are a good candidate for testing with a 224G per second interface. If you want to produce via impedance plots and S-parameter plots like those I've shown on screen, you're going to need a tool like Simbeor. But the great thing about Simbeor is it is specialized for PCBs, and it makes it very easy to produce these kinds of plots. Now, Simbeor isn't the only program that does this. There are, of course, other programs from Ansys and Keysight. Ansys is one that you might use for much more complex structures, or if you need to integrate other features into the simulation environment. But if the only thing you want to look at is the vias and the transmission lines, highly recommend you use Simbeor. Thank you very much, Paul Clark, for tagging me in your LinkedIn post. I'm always happy to answer questions like this. And of course, if anyone out there leaves a great comment or question on one of my videos, one of my LinkedIn posts, or one of my videos on Altium Academy, it might just end up in one of these videos. Make sure to hit the like button, hit the subscribe button. We'll see you next time for more PCB design tips. Thanks, everybody.